Hi, welcome back to the breadboard and another installment of our road test evaluating the DAC8734EVM module from Texas Instruments, which is a quad 16-bit digital to analog converter with multiple modes, bipolar and unipolar outputs, where it can actually have a bipolar output from -10 volts to +10 volts if you want, or a unipolar where it will go from 0 volts up to +20 volts on the output. Very handy indeed. Now, I've already put out a few videos on the DAC8734 as a chip, so I'm not going to give a thorough evaluation of the actual DAC chip itself. I'm going to link in the previous posts that I've done though, so that you have them to watch and everything else. But what I'm going to do here is more evaluate the evaluation module itself to see what's on it, see how well it works, see any deficiencies and things like that there might be there. The other thing I want to mention right off the bat, if Texas Instruments, if you're listening, you need to please review some of the documentation you provide, because in this particular one, you're referring in several places to switch settings, or in one particular place, switch settings to select some of the default inputs to change the mode from unipolar to bipolar, the reset line and the load line, the LDAC line, and you refer to the switches as open, whereas what the reality is you mean on, which from a switch perspective is actually a closed contact. So that threw me for a little bit while I was trying to figure out why this thing wasn't working, until I realized, and I got the meter out and actually measured what was happening with these. And once I figured that out, of course, it was easy to get it working. And then the other thing that I found was that the pinouts on the board, most of them are very clear, and the board, when we go and have a look at the closer view of the diagram, has pins on the top side and sockets on the bottom side, and they're directly mirrored in about 99% of the pins. And there was one pin in particular that threw me, which was the serial input, which from a microcontroller perspective would be the master out slave in pin. It's not mirrored top and bottom of the socket. Everything else is, but in this case it's only on the bottom of the socket, not on the top. The top one is the master in slave out pin, and you know, looking at the diagram initially, it was very misleading, and even in the text of the documentation it's misleading. So after a bit of metering and tracing through the tracks on the PCB, I finally figured it out. So now I have this working. Now, because I've done software before, I'm not going to rewrite anything and do anything special from that perspective. I'm going to reuse the Raspberry Pi software that I used when I was evaluating the DAC8734 chip, and I'm going to hook up the jumper the DAC8734 EVM module so that the software will work exactly as I had used it before. So what I'm going to do now is show you the top diagram, which I've annotated, and I'll provide that in the post as well to show you how I've hooked it up. And I'll also include the software again for the Raspberry Pi that I used, as well as the Arduino and Launchpad software. So you can either get it from the previous articles, or you can just grab it from this one, because I'll have it all attached there. The Raspberry Pi software that I'm using though is running under Windows 10 for IoT on the Raspberry Pi, not under Linux. So just be aware of that. If you don't have it with Windows 10 on your Raspberry Pi, then you'll either have to write the software yourself, which is not too difficult, or use a Launchpad or an Arduino and use the command line interfaces to it that I show in the previous videos. Anyway, let's go have a look at the diagram for the board first. I've got a picture of the top of the board that I've annotated, so I can quickly run you through what's on it. The actual board is got wiring up to the yin-yangs right now, so it'll be more difficult to show you what's happening there. But anyway, the diagram is quite clear, and I will post the diagram as well so that it helps anybody watching this to set up their own and get it running. So let's get to the diagram. Okay, so this is a picture of the top of the DAC8734 EVM module, and what we have here is we have a connector which is J1A. J1B is the one on the back, and it supports the actual outputs of the DAC, which is output 0, 1, 2, 3, and also a monitor output. Now the monitor output is actually buffered via an op-amp so that we don't draw too much current out of that pin, because it's not designed for it. And then on the odd side pin, so 1, 3, 5, 7, 9, they're all connected to ground, so that if you've got the outputs, you know, like in my case, as you'll see in a moment, a boatload of DMMs, you can connect all of the grounds as close as possible to the board without an issue. So that's the output side over on the left hand side here. On the right hand side, this is all of the serial communications and some of the standard jumper settings and things that you would need to hook it up to a Raspberry Pi, to an Arduino, or to a launchpad or any other I/O device that you know, microcontroller interface that you're using. So again, it's pin 1 is the top left here. So pin 2 is a GPIO output, GPIO 0 output from the DAC. And what I've done is I've jumped that into the unipolar bipolar mode pin for side A of the DAC8734. And that's exactly what I had done on my previous software when I was evaluating the chip on a breadboard. And then pin 6, which is GPIO 1 output, I've linked across to pin 12, which is the unipolar bipolar input for side B. Now, in order to be able to do that up here, I also had to turn off the switches that were corresponding to that down here. Now, the description for these switches are the ones that I was referring to that actually are misleading. It says open in the description, and what it really means is on. Now, because I'm using the software and the GPIO outputs of the DAC in order to control the unipolar bipolar for channel A and for group A and group B, I've had to turn off the switches for those two controls so that it just has a weak pull-up to the supply rail. The RST by default is already turned off anyway, and the only one that I've left turned on is the LDAC, which what that does is it allows the DAC to automatically update when you write the data registers. If you turn that off, then you have to just send the relevant bit to the command register to tell it to latch the output DAC and adjust the analog outputs. Now, the only difference there is that when I output one channel via software, it will directly be reflected on the analog output. So if I do 4 outputs, they will actually be out of step slightly with each other when the outputs adjust. Whereas if I use the LDAC software-wise, I can update all 4 registers for the DAC outputs and send one command to the control register to actually turn or to adjust those outputs all in one go. So that's really the only difference there for LDAC, whether you have it on or off, is how you do the software. My software happens to be assuming that LDAC is set hard with the pin on the chip itself. So the other pins that I've got here, so these are 2 just jumpers that I put on the pins here. They're just fixed jumpers. The other ones I've got, which is the SPI clock, the SPI chip select, the master in slave out, and the master out slave in, and the I/O ground. These all go to the relevant Raspberry Pi pins, and I'll include a diagram for hooking that up. Now, the thing to note here, which is what I was mentioning before, is that pin 11, which is 1, 3, 5, 7, 9, 11, yep, this one here, which is SPI MISO on the top of the board, i.e. the side that we're looking at, that's the master in slave out. And on the bottom of the board, in that exact same position, is the master out slave in, and that is the one you want to use on the bottom in order to talk to the DAC chip. All the other pins are actually on the top. You don't need to connect anything on the bottom for the rest of them, which is why I was kind of blown away that Texas Instruments had decided to lay the board out this way. It just didn't make sense to me. Anyway, that's the basic connections. That's all the connections you need to connect to the Raspberry Pi. And you know, if you're using an Arduino or a Launchpad, you just connect them to the equivalent pins on those devices as well. But those are the only ones you need. The last thing that's remaining for as far as connections are concerned are for the supply rails. So what I've done here is I've maximized the potential of testing on this. So I put plus 24 volts to the plus VA, which is the analog plus supply, which is on pin 1 of the voltage header, which is a 10-pin header here. And pin 2 I've put to minus 12 volts. This allows me through software to simply switch between bipolar and unipolar mode and have either plus or minus 10 volt output, assuming I'm using a 5 volt VREF, that is, or use a 0 to plus 20 volt output, again with a 5 volt supply. Now the gain, I haven't changed the jumpers for the gain. The default setting that they've done with this board is they basically hardwired to be at least a ×2 gain, and there's another 4 jumpers. It's jumper 2, 3, 4, and 5, whereas if you link those in as well, then you change the gain to be a gain of 4, I think. Yes, 4. Which means that if you're using 5 volts, obviously you would overshoot the rails and hit them only with the binary equivalent of only half scale. So if you were using a 2.5 volt V reference, then you could put those jumpers in and still get a 0 to 10 volt, or sorry, -10 to +10, or a 0 to 20 volt output, if that's what you wanted. But I've left them as their defaults right now, which is just a ×2. So my 5 volt supply here will give me either -10 to +10, or it will give me a 0 to 20 volts. What else have we got here? We've got the digital ground, which I've connected to a power supply. The analog ground I've also connected to my power supply. So I've got +12, I've got -12, +24, and +5 volts, which is the digital supply for the chip, all going to my Keithley 2230G triple channel power supply. So I'm controlling that separately, and the reason for that is I wanted to be able to see what current was being drawn for each of those supplies, and the analog ground is the common ground connection for the power supply. The I/O plus 3.3 volts, that's coming from the Raspberry Pi, and that's just the interface logic, and you use the same supply here as what the microcontroller is using. So if you put this onto an Arduino Uno, for instance, you would set that to plus 5 volts, and you would adjust the jumper here to be using 5 volts. If you were using 1.3 volts, then that is also handled by a jumper on here, and you can actually feed in 1.3 volts for some gate arrays, or programmable logic arrays and things like that. The idea is that you can go up to 5 volts for the I/O interface, and you just match the supply on the I/O interface to whatever you're using for your microcontroller. So if it's 2.5 volts, you put 2.5 volts in, etc., etc. And that pretty much is all of the connections. The other thing that is of note on here is these two big red slider switches, and what these allow us to do is select either a 5 volt reference, which is a Texas Instruments 5020 voltage reference IC, or a 2.5 volt, which is a 5025, or you can select an external voltage reference. So what I've done for the sake of evaluating this is left it on 5 volts, although as we're running through I will switch them to 2.5 so that you can just see what happens on the output. And like every standard digital to analog converter, your scale is effectively set, or the basic set scale is set by the value of the voltage reference. And then in the case of these D-to-A converters, there is an output amplifier with a gain capability on it as well, which is why we're able to get to either plus 20 volts in unipolar or plus or minus 10 volts in bipolar. Anyway, that's pretty much all of the connections that I have, and as I say, I'm going to publish this diagram so that it will help anybody else trying to hook up all of these things on the web when I post it, and we can go from there. So let's now go to the actual evaluation module hardware and see what we've got. So this is the board here, and as you can see, it matches very closely to what we were saying. Supply rails, I've got plus 5 and 0 volts from my power supply, plus 24 volts and minus 12 volts from the power supply, and then this is the analog ground to the power supply as well. This other black one here is the digital ground for the 5 volt rail to the power supply. I have a 0 volt to the Raspberry Pi over here. I've got the 3.3 volt, which is this white wire, and then the purple, green, and blue are the SPI bus connections, and there's just another ground connection just for good measure there. The bottom green is connecting my SPI data output, my master out slave in, to the bottom of the board. The top blue wire is the master in slave out, which is the data coming back from the DAC back to the Raspberry Pi. Now we don't actually use that in my software, although you could use it to read status registers and things like that if you wanted to. What else we've got here? The two jumpers, we've got a black wire and a brown wire here. These are the two jumpers for the GPIO outputs to the bipolar, unipolar control lines on the DAC, and then 5 multimeters basically hooked up here. I've got 4 multimeters monitoring the voltage directly coming out of the different DAC channels, and I've got my Keysight 34478 7.5 digit multimeter trending one of the analog channels so that we can get some kind of idea of noise and drift over a few minute period on the DAC evaluation module as well. And you know, that's pretty good as far as what the stability is like, because I mean it is a 16-bit DAC, and we'll see that now. So let's just zoom out a bit so we can see the whole scene and continue. I've made it a little bit darker, but at least now you can see the, yeah, that's much better. At least now you can see the multimeters properly. So there's nothing really to do with the DAC here except when I go to change the voltage reference from 5 volts to 2.5 volts. Now right now I've got my control software, which is up here on my screen. This is the exact same software as I had when I was running the DAC8734 test using the breadboard, so I haven't changed it in any way. I've got both channels powered down right now so that I could see the current that's being drawn. And if we go look at my DMM, sorry, my power supply, you'll see that the 5 volts is not drawing anything. My plus 24 volts is drawing 8 milliamps, and the minus 12 volts, which is actually just saying plus 12 here, but it's the way that's hooked up on the banana plugs, is drawing 4 milliamps. Now, this is a very low power digital to analog converter, and it's supposed to be ultra low power when it's in standby mode, like powered down, which is what it currently is. So initially I was curious as to why there are 4 milliamps on the negative rail and 8 milliamps being drawn on the positive rail. And I actually figured that out, and let me just grab a diagram and I will show you why. So this is the full schematic of the evaluation module. We have the DAC itself in the middle here. We've got the analog input channel. This is the digital, the SPI bus and controls where you put the jumpers and things. These are the top. This is the top connector, and this is the bottom connector. I will post a link to the PDF that has all of this in, so you can have a closer look yourself. And the thing to note here, of course, is that pin 11 here is not the same as pin 11 here. This is the analog output connector, and all of the pins here are mirrored top and bottom. You know, there's no concerns about that. And then you've got the power connector down here. Now, these are the switch jumpers here, but why we have power being consumed, or at least the amount of power, the 8 milliamps on the plus 24 and the 4 milliamps on the minus 12 rail, is because we have an op amp here, which is part of the circuit, which is being driven off of that supply, and we also have 2 voltage references which are being driven from a 75 L08, so an 8 volt linear voltage regulator here, which is coming from the plus 24 volt supply and feeding these 2 voltage references, which are then feeding up into here. These are also powered up all the time as well. So all of these three things are all consuming power, which probably is accounting for the fact that we've got 4 milliamps on the negative rail of this op amp, and probably 4 milliamps on the plus rail too, and then these 2 are probably drawing a couple of milliamps each as well, and then there's going to be some insignificant amount of power being drawn inside the DAC too. So that explains why we're not seeing such a low power consumption from the supplies than what I would expect. Now, part of this evaluation module, of course, is that they do claim it's a very low power DAC, and I would have expected at least to have a jumper or something on the evaluation module so that you could actually monitor the power consumption of the DAC chip itself. Unfortunately, this is not the case, so it's not really possible to see how much power the DAC on its own is consuming. You could probably, you know, conservatively guesstimate, you know, while it's in power down mode, assume that it's virtually nothing and go off the data sheets. And if I actually go to the software now, I'm just going to click the power up of group A and group B, and let me just put you back to the power supply, and you can see what's going to happen with the power. So you can see there the 24 volts and the 12 volt rails. So I'm going to power up channel A right now. That's it, just powered up there now, and you can see it's gone from 8 milliamps to 14, so it's added 6 milliamps, and the 4 milliamps has gone to 10, which means it's basically added 6 milliamps to both rails for that one. And now I'm going to turn on group B, and let's see if it goes up by another 6, which it does. So you can see that both these channels are basically, when you power it down, it's dropping 6 milliamps. Now that could vary a little bit depending on the load that you have on the DACs. I don't have any load. Well, I have a 10 megohm load for each of the multimeters that are hooked up, but that's all I've got hooked. So you can see there that you're actually saving quite a bit of power. Just turn them both off again and you'll see it go back down again. Alright, so there's quite a bit of power that you're saving on the DAC itself, but of course your peripheral circuitry is accounting for several milliamps of that power as well. So if you were running on a battery operated system, you may want to put additional switches in to turn off your voltage reference, or well, you might want to leave your voltage reference on for stability, I guess, but at least turn off that output op amp so that it's not consuming as much power, which would help things a little bit more as well. So let's go over now. We're done with the power supply there. As I said, I've got this set so that we can monitor the current being drawn, and so that I could have enough supply rails to try all the modes of the DAC. So let's just go down here, zoom out. Alright, so I'm going to power these both back up again. Now I've already preset some voltages on these, and what I've got is group A is running in unipolar mode, which means it's 0 to 10 volts, and you can see here that the this first meter is channel DAC 0, which I've got set with a digital value of 65535, which is maximum, and as you can see it's reading 19.9 volts. Now I haven't done anything with the calibration registers here, and if you look at the schematics for the evaluation module, there is no trim on the plus and minus on the voltage references either, so they're just at whatever their default values are. Now they're normally pretty accurate, but of course the DAC as well has got calibration registers, and because they're not been set, there is a little bit of an offset that can be calibrated out of the DACs under software control quite easily, because it the voltage rail that you're seeing here coming out, that's 19.900 volts. If I actually just change the output right now, 65535, if I change it to 65534, you'll see that it didn't even change on the resolution of that meter. All right, and just to prove the fact that it is doing something, I'll change it to 32767. You can see there, that goes down to 10 volts, or close to 10 volts anyway. If I put it back up to 65535, I'm not showing you the Raspberry Pi screen because you've seen that on the previous videos. Go back to 65535, you'll see it goes up to 20 volts. If I go to 655, let me take off a whole 10 count, so go 25. And you see that makes 2 millivolts difference on 20 volts, 3 millivolts difference with a 10 count. So if I go 30, right, that brings it up to very, very close, and then 65535 will bring it right back up to the 19.90. So the calibration register will allow you to fix that completely. If I go to, and what each of these DMMs right now, I've got to turn the lights off again, sorry. There you go, now you can see them better. So each of these DMMs have a different value. So this first one, the DAC register is set to 65535, and it is running in unipolar mode. Because these two are both on group A, this one is also running in unipolar mode, but I have 32767 set as the value for this one, which is the obviously 10 volts. This one's got 20 volts. And then the right hand side too, this channel is set into bipolar mode, and as that group is in bipolar mode, it can go from -10 to +10 volts. And you can see here we've got -9.954 and +9.953. So it's fairly well balanced across the plus and minus 10, and that is equivalent to, because it's bipolar, it's effectively 2's complement on the register. So it doesn't go, you can't put in 0 to 65535 on one side. You put in 32768 will give you -10 volts, because that's basically the furthest away from 0 as you can get when you're using the most significant bit as being a sign value. And then 32767, which is only one down from it, is the furthest you can go in the positive direction. So if you think of 0 being 0 volts, and I'll show you this, I'll just I'll set DAC3, which is basically this one. I'm going to set its value to 0, all right, and that's just going to go now. So there's 0, and as you can see, I get, well, 0, which is really nice. Now if I set it to 65535, which is the maximum value, that's actually only -1 count on the whole range. So and it's a 10 volt scale, so of course it makes a little bit more of a difference on the, 1 count does on the meter. So you can see there, that's changed it by having one binary count on 65535. It's made 300 microvolts difference on the output. And now if I go back to setting it to 0, right, it's reading 0. And if I go and set it to 32767, which is as far as you can go, which is all ones except for the most significant bit, then it'll go to +10 volts. And of course if I go half of that, which is 16383, that should be 5 volts, 16383. No, helps if I back off the old value. 16383, because 16384 will be the next bit. So that'll set 5 volts. Now obviously within this I can tweak that now with those values. Say if I make it 16424, 16426, make that a 7, and there you go. So we got exactly 5.000, well, 5.0001. So if I made it 426, probably a little bit too low the other way, yeah, just a tad. But as you can see, you can quite easily get those values that you need, and they're fairly stable. Yeah, so that's working in bipolar mode. Now if I change this to now actually work in unipolar mode, just going to hit the button now, the displays themselves might do some silly things initially until I reset the values. So it's now set to unipolar mode. You can see the right one, which was set to 32767, which was maximum scale when I initially set it, is now showing maximum voltage, but the register is still 32767, which doesn't make sense, but that's because I haven't reset it. And the same for the 5 volt one, it's reading close to maximum because it's still, it's confused because I've changed the mode of operation, but I haven't rewritten the values of the register. So if I rewrite the exact same value, 16384, so there's 5 volts, and if I set the 32767 on DAC, the last DAC, DAC3, you'll see that'll go to 10 volts, all right, or close enough, because as I said, I'm not using the calibration registers. Or if I go to 65535, which is the maximum count, you'll see it's up to 20 volts. Now if I put the mode back to unipolar, you'll see that they've dropped to some funny values again. Oh, the other thing I can show you here, if I put this back to something, sorry, so you've got +10, -5, +10, +20 volts on these outputs. Now when I power these down, that was one of the other features that we were looking at the current consumption before. Now let's just look at what happens to the outputs. I've just powered down channel group B, and you can see both the outputs have gone to 0. And that's one of the features here. It actually puts a pull down resistor that's built into the DAC across the output and disconnects the op amp from it when it powers it down, so that it actually gives a hard 0 voltage on all of the DAC outputs. You can see now I've powered down the other one, they're all now sitting at 0. Now internally the DAC is still remembering the values, and if I power this back up again, it'll go right back to where it was, which is really nice. Now the other thing I wanted to show you, which we're getting close to having a look at everything here, because as I said, we already had a look at the DAC itself, is the stability of this. Let's see if I can get this to line up a little better without reflections. There we go. So what I'm doing here is a trend of the channel 1. I've got the DMM hooked to the same input, and I'm just, what it's doing is it's reading the 20 volt rail that is set right now. So now this is using the Keysight 34470A. One of its features, of course, is that it can trend one of the voltages that it's reading, and what I've got it set to right now is looking at the 20 volt output on DAC 0 to see how stable it is, and you can see it jittering around a little bit. But if you actually look at the display on here, this is 19.90449, so it's down to 10 microvolts resolution on this display. Even though it's reading 20 volts, it's showing this to a resolution of 10 microvolts. So it's between 19.90449 and 5.6, which is only 70 microvolts difference there. If I just auto scale that, clear the values, and we'll start it again. Let it run for a few seconds. We'll come back in just a moment once it's captured a bit more of a screen full. Okay, so this had a couple of minutes of tracking here. Now, as you can see here, it's 19.9043, which means it's 300 microamps there from the 4, and we go up to 6. So that's about 300 microamps full scale on this graph, and you can see here that on average it's doing about 150 microamps or less of noise, a little bit of a dip here. Now, this big spike that you see here, this was actually when I literally just blew from about 12-14 inches away onto the board. Just simply using my own breath, just put a puff of wind across the board, and that caused that little dip. And what it's probably doing is affecting the voltage references slightly. It's only microvolts, but you can see there, if I do it again, you can see it's fairly clean right now. I'm just going to blow on it again. Alright, just blowing it twice. And you can see coming into view now, right here, is there are two little dips that are actually caused from me blowing on this thing. I'll do it again just to prove it. Just do it once this time. And you can see there's another spike. Right? So you can see here that just the breeze in the air can cause a problem. And you can see right now with this, it's my DAC is sitting just on the bench in the open. So these undulations that are here where it's drifting up and down can easily be temperature related, just from the air in the lab, because I'm in a standard house, the air is going to be moving around, and that could be causing this thing to drift up and down. So it could be that the actual noise, the real noise of this, is only these lower values. Now there's really, I guess there might be a, if I can, maybe I can put a box over this. So let me just readjust this a second and come back to it. I'm going to try and put it into a cardboard box or something just to keep the breeze away from it, and we'll do another measurement. I'll disconnect the scopes and all the other meters except for channel 1, just to make it easier. So as you can see now, I put the DAC8734EVM into a cardboard box. This will prevent a lot of air from getting to it and disturbing the voltage references and things like that, and causing temperature variations on the board. And if we now go back and look at the Keysight, which is trending the output of the DVM, we will see something quite remarkable, which will basically should be a lesson to anybody that is trying to measure the stability of circuits in the lab. I haven't adjusted the setting of the DMM here. It is still set with a 300 microvolt full scale resolution. Now before, it was going quite a lot of swinging to and fro, and now that has pretty much almost disappeared. If I blow on it, I don't think it's going to make much difference now, but it might make a tiny bit of difference. Alright, you can see there it's not making any difference whatsoever to the output, and now it is actually staying between 4, 5, and 6. And if I tell this to now rescale so we can get a better view of it, it's basically sitting between 4.5 and 5.5. So now we had 300 microvolts of drift before for this thing. Now there is a longer term drift here because the temperature is still probably varying a little bit just because of the ambient temperature changing in the house and things. But you can see it's nowhere near, it's slowly drifting over time in a single direction. And that probably is because I've just put it inside the box. I haven't let the air stabilize, so temperatures are going to be changing. All right, but it is not swinging around anywhere near as much, and it is now also not susceptible to me blowing on it. All right, it's making no difference at all. So you can see here now, and the range, of course, now is 200 microvolts full scale, and it has only drifted 100 microvolts in about the same period that it was drifted significantly more on the previous example. And it's also no longer now susceptible to me blowing on it. Now obviously it's just in a cardboard box, it's not insulated or anything else, so it's still going to be susceptible to the ambient temperature changing in the lab here. And of course because of that, you're going to see this slow drift over time. But it does go to show you that when you have high accuracy like 16 bits or more, you probably see this on even lower resolution DACs as well, that temperature can play a big part in your measurement accuracy. All right, if you want to be able to get 1, 2, 3 microvolts resolution or better, you better have your equipment well shielded from temperature variations, allow it to stabilize for an hour or so before you do your measurements and testing. The Keysight 34470A multimeter, this one, it recommends that you leave it on for at least half an hour from cold before you start trying to do any measurements, because the internal voltage reference, which in this case on this DMM is actually temperature controlled, has chance to stabilize. And the same thing for any piece of electronics equipment, even my Keithley power supply. When you first turn it on from cold, the voltage references in it are going to need time to warm up and stabilize before they're going to give you a stable output voltage. You can see here now, even on this, as I'm talking, it is slowly drifting down a little bit over time, but it's nowhere near as noisy as it was when I had it out of the box. So anyway, yes, I think from an evaluation board perspective, this DAC8734EVM is a nice way to evaluate the chip from Texas Instruments. It's a shame that they didn't make a better job of the pinouts. I mean, on the analog output side, that's just fine, and even the voltage pinout connector it works just okay for everything you need it for. But the serial line one, I'm not sure why they decided to put the serial inline on the bottom of the board and everything else on the top. I just can't fathom why they did that. And also having the not having the ability to measure the current being drawn by the EVM as well on its own, without considering the two voltage references and the op amp. It would have been nice if there was a way to just measure the current of the EVM, the DAC8734 on its own. The evaluation module, I think it serves its purpose. It is quite easy to use. It gives you a lot of flexibility as to how to set it up. You do need to have at least 3 different supplies. You need a plus and minus analog supply, and you need at least a +5 or a +3 volt digital supply for the board. and then you need a means to hook it up to some kind of controller. You can't hook it straight to a PC or anything. If you had a USB to SPI bus adapter, which they do exist, then you could send commands from a PC to it. Or if you have things like Arduino Unos, launch pads, Raspberry Pis, some of the other ones like a SAM5D4s and all sorts of, numerous different microcontroller boards that have SPI buses on them, then you can talk to this as well. It doesn't take much software at all. I've shown you that in previous articles, and as I said, I'm going to link it in. The stability, even for an evaluation module with no real installation on the voltage references and things like that, is pretty good. As you could see, a couple of hundred microvolts on 20 volt scale is pretty good. And even as we're sitting here now watching this, you can see it's sitting there with 0.99988, and that's staying pretty stable. And its temperature changes, I think, are more caused by the air temperature drifting in this room. I would have to build some kind of insulated box or something to put it in and shield it to see if I can improve on that. There also could be a little bit of noise from the power supplies and things as well that are adding to this. My Keithley triple power supply is fairly good, but it's not a precision power supply. I mean, it is pretty accurate, but it's not like one of the high-end Keysight power supplies where they have the 50 microsecond transient response times and ultra accurate control and everything else. There's a little more general purpose power supply, albeit it's a pretty good one. So there's a few things that could be interfering with it here. But in general, I think the evaluation module is pretty good. As I say, a few little deficiencies in the manual for it, the user guide, that needs to be addressed. So it won't get 100% rating from me for the evaluation board because of their few deficiencies here, like the having to use both sides of the board for plumbing it into your controller, not being able to measure the current of the ADC separate to the op amp and voltage reference supplies. It would be nice if there was just a jumper that allowed you to disconnect the VREFs or power them separately so that you could do it. But minor board changes would fix that. And outside of that, though, it's a pretty good board. It's well laid out. It's got no Bulges or anything like that required on it. It does allow you to test almost all of the functionality of the DAC. Most of what you need really is in software, and the user guide freely says that there is no software specifically written for this evaluation module, but there are plenty of guides for talking to similar devices, both on the internet in general and on TI's own website. But also, now I've also written some software myself which you can use freely to test the board in your own way, and just feel free to extend the software as much as you like. Anyway, that pretty much ends the evaluation of the DAC8734EVM, and a little bit more of a look at some of the capabilities of the Keysight 34470A 7.5 digit multimeter. Basically the trending capability, so that you can look at voltages over time. Even if you're looking at a high voltage, you can still look at down to microvolt changes even on, say, a 20 volt signal, which is pretty awesome. Anyway, I will call it quits for that, and maybe this will be a shorter video than normal. So anyway, any questions, just let me know. Send me an email, make a comment in the comments, whatever you need to, whatever suits the system that you're viewing this on. And there'll be more videos coming out shortly for the Keysight 34470A digital multimeter.